everybody. Welcome to today's session. Today we will be learning about exponents and exponent rules. Okay. First of all, what is an exponent? Exponents are just repeated multiplication in the same way that multiplication is repeated addition. Exponents are just repeated multiplication. So the bottom number or base is the number getting multiplied. The top number, the exponent, tells you how many times it gets multiplied together. Let's look at some examples. So first, 2 to the 5th. This would mean 2 times 2 times 2 times 2, 5 times. Okay. The idea here is that the 2, just to use the terminology from above, the 2 here is the base. All right. And the 5 is the exponent. Okay. 2 is the number getting multiplied, and 5 is the number of times. Okay. The next example is 3 squared. 3 is the base, or number getting multiplied. It's getting multiplied together twice, so 3 times 3. And finally, x to the 9th. X, again, is the base, n is the exponent, and so it gets multiplied together 9 times. All right. So that's what exponents are. That's great. What happens if we try to combine multiple expressions, each of which involves exponents? So here are a few examples. First, how about 2 to the 4th times 2 to the 5th? Well, we know that 2 to the 4th can be written as 2 times 2 times 2 times 2, 4 times. 2 to the 5th is 2 times 2 times 2 times 2 times 2, 5 times. So altogether, if we're doing it 4 times, if we're multiplying first 4 times and then another 5 times, that is a total of 9 times, or we could write that as 2 to the 9th. Or if we were doing 3 to the 5th divided by 3 to the 3rd, that's 5 3s on the top, 3 of which will cancel with the 3 3s on the bottom. And so overall, we're left with just 2 3s being multiplied. Whoops. And so when we simplify this, it becomes 3 squared. Okay. And then finally, x squared all raised to the 5th power means that we're multiplying x squared times itself 5 times, like this. X squared multiplied by itself 5 times, because in this case, the base is x squared, itself involving an exponent, and the exponent is 5. Okay, so x squared times itself 5 times, and if we count up how many total x's are getting multiplied here, 2 for each of these x squared expressions, so that's a total of x to the 10th. Great, so hopefully all of that makes sense. And for expressions that combine multiple exponents, we could always go through like this and combine the different expressions piece by piece. But it would be nice if we had some more general rules. Okay, if we had some shortcuts that we could use instead of having to break things down into their components and then recombine every single time. And notice that this 4 and this 5 add up to give us 9. 5 minus 3 here gives us 2. And in the third example, the 2 and the 5 multiply to give us 10. So that'll be the basis for the general rules that we're about to see on the next slide. So exponent rules. Okay, so here are the rules. When we do the thing in purple to an expression, then we do the thing in blue to the exponents that are involved. Okay, so anytime we, let me get my cursor out here. Anytime we multiply an expression, or two expressions involving exponents, we will add together the exponents involved. Anytime we divide two expressions involving exponents, we will subtract. the two exponents involved. And anytime we raise an expression involving exponents to a power, we'll multiply the exponent times the power that we're raising it to. All right, so multiply, add, divide, subtract, and power multiply. Those are the rules. Here's a handy mnemonic that really just rolls off the tongue. MADSPM, okay, to help you remember. Multiply, add, divide, subtract, power multiply. So we can see a few examples. 2 to the 4th times 2 to the 5th. In this case, we're multiplying. Let me switch back to my pen. So in this case, we are multiplying. And so, therefore, we add the exponents. Okay, 2 to the 9th. In the second example, 3 to the 5th divided by 3 to the 3rd. We are dividing the two expressions. And so we subtract the exponents. And in the final example, we're taking an expression that involves an exponent and raising it to a power. And so in that case, we multiply the exponent times the power that we're raising it to. All right, so those are the exponent rules. If you know these, then you can handle any expression involving multiple exponents. So let's do some practice. I'll give you guys a minute to work through these 5 examples. So grab a pencil and a sheet of paper, if you would, and take a minute to work through these 5 problems, applying the rules that we saw on the previous slide. Okay? I'll give you guys a minute to work through these 5. Okay, no worries if you are still working. Hopefully you got a good start though on working on these 5 examples. So let's go through and cover them together. So first, number 1, we're cubing the entire expression inside the parentheses. So one of the key things is we need to remember that the cube goes both to the 3 term, or I'm sorry, both to the 2 rather. So that's 2 cubed multiplied by x squared cubed. Okay, so the cube distributes over both terms inside the parentheses. We know that 2 cubed equals 8, because that's 2 times 2 times 2 times, now we use the power multiply rule. We're raising x squared to a power, and so we multiply the exponent by the power we're raising it to, and 2 times 3 is 6. So the answer is 8x to the 6th. For number 2, first I'll just leave the 3x squared alone and only worry about the second piece. Ooh, in that second piece, 2x squared cubed is the same as what we had above. So I already know that that's 8x to the 6th. Now I just need to multiply these two together. I'll multiply like terms. 3 times 8 is 24. X squared times x to the 6th. We're multiplying two expressions with exponents, and so we add the exponents together. 24 x to the eighth. Okay. Next, number 3. Um, Once again, just like in the first one, I need to distribute the square outside the parentheses to both terms inside the parentheses. X squared squared. Again, that's we're multiplying, or rather, we're raising to a power. And so, sorry about that. Looks like we had a momentary technical difficulty. My computer was telling me I got muted for a second there. So hopefully that was only for a second. I was just saying this first term is x to the fourth. This second term is y to the fifth squared. Again, this is a power. So if I'm raising an expression with an exponent to a power, then I multiply x to the fourth, y to the 10th. Fourth example, I'll take this first expression first. I need to square both terms inside the parentheses. That's the same as we saw above, x to the fourth, y to the 10th. Then the second term, ooh, I've got some negatives here, but it just works the same way. The rule still applies. I'm raising expressions with exponents to a power, so I just multiply, and we know how to multiply negative numbers. So -2 times -2 is 4. So the first term is x to the fourth. The second term is 2 times -2, y to the negative fourth. Now I use the multiplication rule for exponents to combine these. X to the fourth times x to the fourth is x to the eighth. Y to the 10th times y to the minus fourth is 10 minus 4, which is y to the sixth. All right. And finally, one example to practice division. Um, I'll break this up and do the x's and y's separately. So it's x to the third divided by x times y to the fifth divided by y squared. And remember, when we're dividing, we subtract the exponents. So x cubed divided by x is x squared. That didn't look too much like a squared. There we go, x squared. And y to the fifth divided by y squared is y to the third. Okay. Math is all about practice. It's the best way to learn. So hopefully that practice helped consolidate those rules for you. Now let's talk about a couple of special cases. First, anything to the 0th power is 1. So for example, 2 to the 0th power is 1. 10 to the 0th power, still 1. This ridiculous number that I made up to the 0th power, still 1. Okay? Anything to the 0th power is 1. The idea there is, since the exponent tells us how many times we're multiplying the base times itself, if we're not multiplying the base times itself any times 0th power, then we're just left with the multiplicative unit, or 1. Okay? But you can just remember the rule. 0 to a power is always 0, because we're just multiplying 0 together. And whenever we do that, no matter how many times, we always get 0. Okay? Finally, 1 raised to a power is 1, regardless of what that power is. So 1 squared is 1, 1 to the 10th is 1, and 1 to, 738 million or whatever is still 1. Okay? Let's talk about negative exponents. The rule for these is that negative means reciprocal when it comes to exponents, or more precisely, a raised to the negative n, where a is an arbitrary number, is the reciprocal of a to the n. Okay, so let's see some more concrete examples. X raised to the negative first power just means 1 over x. Since that negative, let me grab my cursor, that negative in the exponent just corresponds to taking the reciprocal. So this is 1 over x. Next example, what if it was x to the negative 2 power? Well, the negative still corresponds to taking the reciprocal, so we get 1 over x squared. Or if it was x to the negative third, it would be 1 over x cubed. Notice, you might notice that this rule switches between the multiply and divide rules. So for example, x to the fifth times x to the negative second is x to the 5 minus 2, which is x to the third. That's using the multiply rule. Or instead of using the multiply rule, I could switch to using the divide rule by exchanging x to the negative 2, right? By exchanging x to the minus 2 for 1 over x squared. And then I'm dividing x to the fifth
35
divided by x
millimeters.
squared, which dividing is subtracting, so x to the 5 minus 2 is x to the third. These are both valid ways to do the problem, and my point here is showing you the connection between these two rules. Um, the fact that this negative equals reciprocal rule gives you the connection between the multiply and divide rules, in case that helps you remember. Okay. Um, um, Next, fractional exponents. So here's the rule for fractional exponents. The denominator, which means the bottom part of the fraction, the thing that we're dividing by, um, is the root. Okay, so here are a couple of examples. X raised to the 1/2 power equals 1/2. Or I'm sorry, equals x raised to the 1/2 power equals the square root of x, I meant to say. X raised to the 1/3 power equals the cube root of x, um, and so on. What if we had the cube root of x squared? Cube root of x squared, well, the x squared in the interior here, in the argument of the root, is getting raised to the 1/3 power. I'm just going in the opposite direction. So x squared to the 1/3 power. And then if we're raising this exponent to a power, we multiply. So 2 times 1/3 is x to the 2/3. All right. Um, so you can remember this fractional exponent rule using the multiply rule, if it helps you remember, x to the 1/2 multiplied by x to the 1/2. Using the multiply rule, this is 1/2 plus 1/2, so x to the first power, which is just x. So I'm multiplying together these two different terms, x to the 1/2, multiply them together to get x. So each one of them must be the square root of x, since we know that the square root of x times itself gives us x. All right. So let's finish up with a few last examples, and then we can do some questions. First, 1 raised to some big power. Well, we know that 1 raised to any power is always 1. So just 1. Negative 2 raised to the third power. Well, this is negative 2 times itself 3 times. We know that 2 to the third power is 8, and we have 3 negatives. 2 of them cancel, so we get negative 8. What about 81 to the 0th power? Okay, remember, anything raised to the 0th power is always 1, because this is like saying we're multiplying 81s times each other. And when we don't multiply any 81s, we're just left with 1, since we're not multiplying anything. 0 squared is just 0 times 0, and 0 times 0 is 0. 6 to the minus 2. Remember that negative exponents correspond to reciprocals, so this is the same as 1 over 6 squared. And 6 squared is 36, so 1 over 36. 25 to the 1/2. Remember that fractional exponents correspond to roots, so this is the same as the square root of 25. And the square root of 25 is plus or minus 5, because negative 5 squared would still be 25, so either one of those. Finally, x to the 6th plus x to the 6th. Top part is, oops, 2x to the 6th divided by x to the 3rd. And now that I've added the numerator, or the two expressions in the numerator together, I can now simplify using the division rule for exponents. Remember, when we divide two expressions with exponents, we subtract the exponents. So this is 2x to the 3rd. Thank you very much for joining us today. I'd like to open the floor up for questions. And I did see one question come in from Lakshya during the lecture. The question was, is 0 raised to the 0 power 1 or 0? Ooh, okay, yeah, that's kind of a fun one. So 0 raised to the 0 power, because we seem to have two conflicting rules, don't we? So Lakshya is noticing something very smart, right? Very clever noticing, which is that we said that 0 raised to any power is 0, but we also said anything raised to the 0 power is 1. So is it 0? Is it 1? Right? It's a very good question. Equals dot 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 0 question mark 1 question mark. Answer. Dun dun dun. Drum roll. It depends. So unfortunately, the answer is that this is not defined. Raising 0 to the 0th power is similar to dividing by 0. There's not a unique answer. Technically, like when you take calculus, you could look at this through the frame of there are different ways to take this limit. If we consider the function x raised to the x power and take the limit as x goes to 0, then depending on how we choose to take that limit, we'll get different results for 0 raised to the 0th power. But the answer is just, this one's not defined. 0 to the 0, not defined. Similar to dividing by 0, you just can't do it. Aditya asks, would you do plus or minus for all even roots? That's a great question, Aditya. So for example, let's say we had the fourth root of 81, just to pick an example. So even root, so that's like the square root, fourth root, things like that. So in this case, the answer is yes. You would always do plus or minus. So this would be plus or minus 3. And that's because either plus 3 raised to the 4th power gives you 81, or minus 3 raised to the 4th power would still give you 81. And so either of these could be fourth roots of 81. Sometimes from the context of the question, Aditya, you would only need either the positive or negative root, like the question could ask you for positive square roots or positive fourth roots. But in general, that's exactly right. For any even root, either a plus or a minus will work. Great question. Ooh, in fact, once you guys go a little further in math, maybe I shouldn't get into this, but with imaginary numbers, plus or minus 3i would also work as fourth roots of 81, but not as square roots. But again, that comes a little later in math. So don't worry about that. It's a very good question from Aditya. Any final questions? Oh yeah, good question. So why can't square roots be negative? So let me create a new slide since this one is going to get a little messy. So let me open up my little whiteboard here. Um, Here we go, loading. Great, perfect. Somebody asks about square roots being negative. So let me know if this answers the question. Let's say we wanted to take the square root of minus 4. Okay. Maybe this is what you meant. Why can't we take the square root of a negative number? Okay, why can't the argument of the square root be negative? Well, I don't know. Let's see. Does it equal 2? If we try, I'll switch to a different color. What if we try 2 times 2? Well, that's 4, right? Not negative 4, and we need to get negative 4. What about if we try negative 2 times negative 2? Could this work as the square root of minus 4? Ah, 2 negatives multiply to a positive, so this is still positive 4. So, how do we get negative 4? As long as we're just restricted to the real numbers, which means all of the numbers from, you know, like minus infinity to infinity. That's supposed to be a 0 in the middle. As long as we're restricted to these normal real numbers, we can't. Okay? Whether we choose positive or negative, when we multiply them together, we can't do it. Okay? Equals does not exist. Now, once you go a little further in math, people really want to be able to take square roots of negative numbers, and so they invent some new types of numbers that allow you to do this. But as long as we're restricted to these, then there aren't any. Okay, so we say that the -4 has no real roots. All right, any final questions before we wrap it up for today? Um, okay, yeah, request a lesson for odd roots, absolutely. So I'll do something pretty similar to like we just saw for even roots. Let's look at, so this is a square root, right, which is even. Let's also talk about odd roots. Okay. And then two variables inside the parentheses. How would this be solved? Okay, great. I'll do both of those. First, I'll do the odd roots though, and then I'll answer the question that came in below. Okay. Let me just move this around to make some more space for myself. I'm going to get rid of my number line since we don't really need that. And I'm going to move this up here. All right. So now and I'll change colors. All right. So what about odd roots? Okay. So let's say we had the cube root instead, and let's say it's a negative number, because I think that's what the question is about. We talked about negative even roots. Let's talk about negative odd roots. So let's say we had the cube root of -27. I know the cube root of positive 27 is 3, because 3 times 3 times 3 is 27. But what if it's negative? Well, let's try it. Let's see, what if we had -3? Does that work? And let's say that I raise this to the third power. Because if it gives me -27, then -3 is the cube root of 27. All right, so -3 times -3, running out of space for my 3, sorry, it's kind of messy, times -3. Let me try that again. Um, when you multiply them together, you do indeed get -27. Uh, all right. Okay, so -3 cubed does give you -27 because two of the negatives cancel and the third one is left over. So the cube root of -27 is just -3. And that's how it works for all odd roots. Let's say we had instead, for example, the the 11th root, just like making something up, of 2048. Okay, uh, 11 is an odd number. 2040, or sorry, I meant minus 2048. If you multiply 2 times itself 11 times, it turns out you get 2048. So this just equals -2. It's an odd number, and so we end up with a negative, so we're able to take the 11th root of this negative number. So I hope that works for odd roots for you guys. Let me know about follow-up questions, but I have one more, and then I will wrap it up with this one. So Patel asks, or maybe, yeah, I think Patel looks like the name that was copied here. What if there are two variables inside the parentheses with an exponent? Okay, this is a great question. So I'm going to add a new whiteboard to work on this one. So like, what if we had x to the fourth? So Patel asks, what if you have x to the fourth, y to the sixth, all raised to some power like this? How would this be solved? It's a great question. Okay. I think that's what was being asked. If it was copied over, right? So we need to apply the third power to both terms. So this cube, in other words, this cube has to be applied both to x to the fourth and to y to the sixth. So that looks like x to the fourth raised to the third power times y to the sixth raised to the third power. And x to the fourth to the third, now we're taking an expression with an exponent, the x to the fourth, and we're raising it to a power. So anytime we raise an exponent to a power, we multiply. Right? Remember the power multiply rule. And similarly, y to the sixth is being raised to the third power, and when there are powers, we multiply, and 6 times 3 is 18. Okay? And so that's the answer to this one. I hope that's what you were asking, Patel. In case you were asking about something like this, if we're adding here, we cannot just distribute normally. We'd have to FOIL it out, equals FOIL, which is a separate topic. Okay? And we'd have to multiply out all of these terms, and it would get kind of messy. All right. Thank you, everybody, for joining today. I hope you all enjoyed it. I had fun teaching you. We do these each Monday. We alternate between math and English. So yeah, so join us again. And thank you very much. I appreciate it.